This lab surrounds the concept of constant velocity. If an object is in constant velocity, it is basically moving in the same direction at the same speed, meaning it does not accelerate, decelerate, or change directions. In essence, this also means that there is a net force of zero acting upon the object, allowing it to stay in the same speed. In order to exhibit this motion, I decided to roll a soda can and capture the movement to quantify on Tracker. As you can see, the soda can rolled smoothly across a wooden table in the negative x direction for about 1 second. It also seems to be moving in a constant speed. Using Tracker, I analyzed this motion to confirm my observation of the can's constant velocity. The length scale, 0.065 meters, was based off of the diameter at the bottom of the can. Starting at 0 seconds, the motion of the object is recorded against an xy coordinate system, moving in the negative x direction with an initial position at 0, 0. With a total of 26 data points, a position versus time table was synthesized and used to plot a position versus time graph. As an entirety, this graph seems to have a straight diagonal line in the positive t, negative x plane, corresponding to the constant increase in time with 0.033 second time intervals and the backwards movement of the object, resulting in the negative x values. The straight line on the graph refers to a constant slope, which, when calculated, refers to the velocity of the object. The average velocity of the object was negative 0.223 meters per second, which could also be calculated by taking the average of all the individual velocities from the data positions in time. It is also noticeable that the velocity of the object is negative. This simply refers to the negative direction in which it is traveling. Now, experimentally, this graph was created to illustrate and analyze the observations that were made. However, if we want to predict the future as to how the motion of the object might appear in later times, we can construct a computational model. Through VIDLE and the Lab1 code template, I adjusted the code so that it would model the observations we made from Tracker beforehand. The basic outline of the code stayed the same, with just a few modifications to the initial conditions and assignments within the while loop. Underneath initial conditions, in accordance to the collected data, the mass was changed to 0.340 kilograms. Initial position was changed to 0, 0, 0. Initial velocity was changed to 0, 0, 0. The starting time was kept at 0 seconds, and delta t, or change in time, changed to 0.033 seconds. Under the while loop, the net force, or F net, was changed to 0, 0, 0. Since there is constant velocity, the net force is 0. Later, in order to predict the ball's velocity and position as the time changes, ball.vel and ball.pos were modified so that they represent the formulas that are used to calculate velocity and position, which is final velocity equals initial velocity plus the net force divided by the object's mass multiplied by change in time, and final position equals initial position plus the object's velocity multiplied by the change in time. The while loop reiterates this function over and over again until it reaches the final time value, 0.833 seconds, so that this updates the velocity position at each time interval. The output shows a graph which looks distinctly similar to the one formed in Tracker. The computational model of the object moving in the negative x direction also looks similar to the video of the rolling can. Finally, here's a graph of the combination of both the experimental and model data. The blue dotted line represents the experimental data, while the red solid line represents the model position. They have similar characteristic of a straight line with the negative slope, and are almost at the same positions. The only discrepancy is in the experimental data where there are a few bumps. This was probably due to the fact that the object did not move in exactly a straight line, which is through human error. Though several trials were taken, even the best trial of pushing the can did not produce a straight line, therefore causing a little shakiness in the position versus time graph and small difference from the model data. Overall, though, the two lines are similar enough to be able to use the model data to predict future positions of the soda can and conclude that the can was traveling in constant velocity as visually proven by the straight slope.